Hello and welcome. Hope you're well. Last video for today, I swear. So in this video, I'm going to look at interpolation methods. Specifically, I'm going to look at lerp, slurp, and nlerp. Great naming convention, by the way. So what are they? Lerp, I'll give you the short one. Lerp is linear interpolation of a vector between 2 points, between two other vectors. Slurp is not just something that I do at the bar when it's happy hour. Slurp is spherical linear interpolation. We'll get into that. Basically, it interpolates the angle. And nlerp is normalized linear interpolation. It's an approximation of slurp, little less robust, little more performant. But anyway, let's get into it. So, lerp. Imagine that we have two vectors, position vectors, A and B. And just for clarity, I'll put the origin here, but we don't need the origin, just, if it helps. So linear interpolation is basically finding a linear function that corresponds to these two endpoints. So when t equals 0, we're at point A. When t equals 1, we're at point B. So if we were to look at the line, it would go along here. So just pick a point here. This is our general P. We're somewhere between these two. And pretty much it goes like you would expect. We'll get a linear combination of A and B. The coefficients for that linear combination are 1 minus t for the A point, and this sets it up so that when t equals 0, it's just A plus t times B. And then we can see, okay, when t equals 0, it's 1 times A plus 0 times B. When t equals 1, it's 0 times A plus 1 times B. We have that t... I don't know if that's just restating the obvious, but it's good to be explicit. Okay, so that is lerp. Now for slurp, imagine pretty much the same scenario. So we have our origin and the points A and B, but now there is some angle between these two vectors, and as we spin around, imagine that we're actually like spinning on a circle. So we are interpolating the angle between the two. And we could say, well, hey, in 2 dimensions, it's really easy, just interpolate the angle. But the thing with slurp is it actually generalizes to higher dimensions. So if we were to do this in 3D, imagine the surface of a sphere or something, some point, some other point, it would actually be generalizing along the surface of the sphere, which is pretty cool. So it turns out, here's my point P, it turns out that the formula for P is given by there we go. It's given by this expression here. I got this from Wikipedia. There we have it. So let me just quickly verify. When t equals 0, we have sine of theta over sine of theta, which is 1. And then we have sine of 0 over sine theta, which is 0. Yeah, that seems to work. Very nice. Not super satisfying. So what I will do is I'll just run through a derivation of this. So the first step is to recognize that we have two vectors with some angle between them, and we are linearly interpolating the angle. So if we look between these two, then that would be an angle of theta. And then if we pick some point somewhere, we say, okay, well that angle theta breaks into two subpieces. This is a little weird. So the way I'd explain this is that this part here has a size of t times theta, and this part here has a size of t theta. Now that seems a little opposite, but hopefully you can see, oh sorry, it's the same thing, isn't it? That's 1 minus t times theta. Okay, hopefully you can see that yes, this is a linear interpolation on theta, and when t equals 0, this angle here is 0, and so the point is corresponding completely with A. And when t equals 1, this angle on this side will be 0, and so it's corresponding completely to the point B. Okay, so that's the first part. Then the next part is a little funky, a little esoteric, but when this made sense to me, the whole method became really a lot of fun. And what I'm dancing around right now is we're basically going to construct an orthonormal basis. So an orthonormal basis is a set of, well, in our case it's two vectors, even though this could be n-dimensional or 3-dimensional or 4-dimensional, who cares? It ultimately is some sort of transformation of a 2-dimensional vector system, because however these two vectors are oriented, I can always sort of spin them around and put them flat on the plane. So in that sense, I just need two basis vectors in this orthonormal basis. I'm going to call this basis vector x and this basis vector y, but that's just my naming convention. They don't have to correspond. Well, they won't. They won't correspond, but I'm talking too much. So the point that I'm getting at is that when we are lined up completely with the x basis vector, we will be completely on the point A. And then as we approach the y basis vector, we'll be coming up towards B. And so you can imagine actually taking this system and reorienting it so that the x basis vector is actually on the x-axis. And this will make things a little easier to visualize. Okay, so again, we have the point A and the point B, and just for not yet, I'll get to that in a second, but actually, yeah, just for simplicity, I'll just assume that we can normalize these vectors. Of course, linear slope doesn't make much sense unless the vectors have the same magnitude, otherwise how can we rotate from one to the other? But I'm talking too much. So here we have some intermediate point, P, and then we say, okay, what's the angle here? Well, the angle here is t theta. Okay, so the point P is on the unit circle. I mean, if we cast this down, it's a right angle triangle. It's on the unit circle, and so its coordinates are cosine t theta times the x basis vector plus sine t theta times the y basis vector. And the goal now is to find x and y, and then we can put them back in and find the actual expression for the point. So we know straight up that x is equal to a. And now in order to find y will essentially be the rejection of b. In other words, if we were to take b and from b subtract the projection onto x of b, that's what's called the rejection. Little side note, because I think it's good to talk about. So if we have two vectors, this is just general background. There we go. U and v, they look pretty similar, but the vector v can be expressed with regards to the vector u. So the vector v breaks down into a vector sum of a part of v which is parallel with u. It's called the projection of v onto u, and it's that plus the part of v which is perpendicular to u, and that's called the rejection. It's all the bits of v that don't line up with u. So if we were to sort of break this up, we have the projection of v onto u, if you imagine dropping that down, and then we have the rejection of v from u, if you imagine removing everything that's in common. I'm not sure if that either made sense or I'm just rambling or saying really basic stuff, but yeah, that's what I'm doing here. So if we take the vector b and we remove all the stuff that's parallel with x and a, then what's left has to be y, basically. But it's not exactly y because we need to normalize it. So take that result and then normalize it. I'm rambling. So let me just put in the numbers here. So what is the projection of b onto x? Well, the projection of b onto x is the inner product. It's the inner product of b and x, which is really a. That'll give us a scalar. And then if we multiply that by the vector a, that will make sure the result is in the direction of a. But then remember that the inner product between two vectors, it's the dot product, it's the magnitude of one times the magnitude of the other times cosine theta. And we know that the angle between these two vectors is theta. So we have the magnitude of a, which is 1, times magnitude of b, which is 1. So it's 1 times cosine theta. And so what this comes down to is b minus a cos theta, but then remember that we still need to normalize that whole result. And so the norm of a vector is the square root of its inner product with itself. So again, this comes down to, we'll just write out the expressions, all of that, divide by, there we go, the inner product with itself. Whew, this is going to get messy. Okay, let's do it. Okay, so the inner product is a linear operator. What that means is that we can just imagine expanding all of this out. As a matter of fact, I'll do that expansion. Oh, this should be angle brackets. Okay, so we have there we go. It's all square root, the denominator. This is a bit of a nightmare. I should be flicking over to a new page, but I am stubborn, so we will continue. Okay, so again, all I did here is I just split up this first term of the inner product. Because it's a linear operator, we can say it's inner product of b with this, we got that, and the inner product of that minus a cosine with the rest. Okay, so let's continue splitting that up. So then we have the inner product of b with b, and I'm just going to skip all the subscripts and stuff, it's all vectors, plus we have the inner product of b with this negative a expression, and then here we'll have negative a inner product with b, so we have two lots of this expression. And then we'll also have the inner product of that negative a cos with itself. Square root. Okay. Now I really will flick over to the next page. Okay, so we have the inner product of b with itself. Now remember, inner product of something with itself is its magnitude squared, and b has a magnitude of 1, so this term really comes out to 1. And then this term, just pull this out, cosine theta is a scalar, so this comes out to 2 cos theta. That should really be a negative, shouldn't it? Because it's that negative a. Okay, so negative 2 cos theta times a product with b. And remember that a product with b is the magnitude of a, which is 1, times the magnitude of b, which is 1, times cosine of theta. So really this is equal to cosine theta. So then if I put that back, I have 1 minus 2 cos squared theta. And then if I look here, well, this is really negative times negative cancels out. So we have cos squared theta times a with itself, which again comes out to 1. So then really what I'm getting at is we have plus cos squared theta. Okay, cool. Well, of course, this stuff really comes out to 1 minus cos squared theta. And 1 minus cos squared theta is sine squared theta, because, of course, cos squared plus sine squared equals 1. Just rearrange that, you get the thing. So what I'm getting at is we have b minus that over the square root of sine squared theta, which is sine theta. Okay. So remember, that is the y basis vector. And just as a refresher, the x basis vector was a. Okay, so our point is, what was it? It was cosine t theta times x plus sine t theta times y. Okay, cool. So now what I'm going to do is I'm going to group things according to the common vectors. So I say, what do I have multiplying a? So for a, yeah, I think that's right. Okay, let's find out. So for a, we have cos t theta from this term, but then we also have this minus that. So that's our a term. And then for the b term, we have that expression there, sine t theta. Okay, now it's starting to almost look like what we have in the equation. I guess we just don't have the absolute values, and that cannot come down to the way the angles are measured, because this is not taking into account the orientation of the angles. Whatever, I'm fine with that. That's a concession I'm going to take. If I had, if I had more time, which I do, but I'm happy with this derivation. Okay, so enough rambling. What can I do? What can I do? I'm going to get this under a common denominator. So I'm going to say, okay, I'm happy with b. It's actually the correct expression. I'm just going to work with a. So if I were to look at the a term, it's something like this. We have cosine t theta like that. Okay, and you may recognize that the numerator has the form, I always get this wrong, so I'll just write the general form. I think it's something like sine of a plus b is sine a cos b plus cos a sine b. If we see the same angles, but just things are flipped around, then if we change that to sine of like a minus b, then yeah, that works, because cos of negative b is positive, whereas sine of negative b is negative. Yes, that will bring in that minus. I'm talking to myself. Why am I doing this? Okay, so this is, what I'm getting at is we have 1 theta and t theta, and this comes out to 1 minus t theta. That's the trig identity there. And then there we have it. That's the expression that we were after. Oh, what an accomplishment. Isn't that cool? Let me just step back through that. I really appreciate this derivation. So again, what we started from was the linear interpolation of the angle between the two vectors. and then we constructed an orthonormal basis. So if you're at the vector A, it's like you're sitting on the x-axis, and then you flip around to the y-axis to get to B. And then we worked out what those basis vectors were by, well, this is actually the Gram-Schmidt process, right? Because you start with a basis vector. Start with the basis, first angle is the basis. First vector becomes the first basis vector, and then the second basis vector, we subtract the interaction with the existing basis vector. And if we had more, we would just keep doing that. That's the Gram-Schmidt orthonormalization process. But yeah, anyway, I will be quiet, but I just think that's so cool. Okay, so how about lerp? Well, when we interpolated between 2 points, actually, imagine that the length of these vectors is 1 at each point. But then when we go in between, it's something else. The length is definitely less than 1. And so if we perform linear interpolation and yet we normalize at every point, maybe it looks a little like this, then that will, in theory, do a pretty good approximation of spherical linear interpolation. And so the formula is basically, the point is the standard, what is it? Linear interpolation. Alrighty, but then we also normalize it. So we divide by, I'll just write this, the norm of the point, which, as we saw before, is basically the square root of the inner product with itself. But yeah, so like I said, this normalized linear interpolation is a little less computationally heavy than the spherical formula, but it is a little less numerically robust. It doesn't work so well for large angles of separation. But yeah, there we have it. I wanted to do an intellectually serious video. I hope you enjoyed it. I definitely did. And yeah, as always, have a great one, and I'll see you around. Bye.